we're going to start doing second order linearity. So chapter 1 is first order, chapter 2 is second order, chapter 3 is n order. No dogs today. No, they're out romping around. My Gingy dog hurt her foot, so she's kind of limping around, so she's just out. So we'll be doing second order, and then in chapter 3 we're going to do n order. So just any order, as long using the same methods, because if you can do second order, if I can teach you how to do third order, you can do 50th order, technically, if it allows it to do such things. So we're going to talk about second order, and so we're going to start with linear. We're going to say it's linear. So linear looks like the following. So it's going to be y double prime. So this is the second derivative, some function of x, y prime, and then some function of x again. So p of x, q of x on y, and then r of x. And it's homogeneous if r of x is equal to 0. It's nonlinear if you can't write it in this form. So let me state some things which are linear and nonlinear. Or let me just give you a couple example things and state what they are. So here I have y double prime plus 25y prime plus cosine x y equals 3 sine of x. That's a funny looking sine. Sine of x. And this is linear. So I'd say this is linear because here 25 is a function of x. Cosine of x is a function of x, and this is a function of x. And so this is linear. It is, in this case, it's non-homogeneous. So we say this is non-homogeneous. Homogeneous. So it's linear, it's non-homogeneous, and it is second order. All right, so let's look at this. So here we have x on double prime plus x y prime plus x y equal to 0. And so notice that this can be rewritten. So if you have anything up here, if you have any function of x up here, you can just divide it out and get it into this form. So here I can just divide this out. So I'll have, this is the same as y double prime over x plus y, because we divide out the x, equal to 0. So this is second order, this is linear, and this is homogeneous. So sometimes you might need to do something to get it into this form, homogeneous. And the last one, I'll just show you something. So here I have y double prime times y plus y prime squared equal to 0. This is nonlinear, right? This is nonlinear for a lot of reasons. So let me, nonlinear. This is nonlinear because here I have a y double prime times a y. So anytime there's y anything times y anything, prime, double prime, whatever. Gee, this is really bad notation, isn't it? Y. My y's look a little bit like g's. So hold on. This is y prime squared. Get rid of it. There we go. So here, if I have y double prime times y, that makes it nonlinear, just does. And if I have y prime squared, that makes it nonlinear. So if I have any powers on this or I multiply it, any of this will make it nonlinear. All right. But let's look at this. Can I solve this ordinary differential equation? Let me rephrase that. If the question is, can I solve it? Most of you will answer, yeah. I trust that the professor knows how to solve this, right? Can you solve this ordinary differential equation? Let me rephrase that. My little friend who just missed that, I still have it up. I marked yours here. Okay. Can you solve this? What's the answer to this? Anyone have a guess? Put it in chat. Y equals 0. Y equals 0 is a solution. Legit, that is a solution. It's not even one I thought you'd come up with, but it's 100% true. Because 0 plus 0 equals 0. Ta-da! Can anyone think of another solution? A non-trivial. We call this the trivial solution for a homogeneous equation. This is always going to be true. So we call this the trivial solution. And in fact, it's so trivial that when we look for two separate linear independent ones, we never consider this one because it's not technically linear independent. But that gets into that. Does anyone think of another one, another function, which if I take its function, if I take a double prime of the function and a function, and I add them up, I get 0. Does anyone have a clue? Or another way of saying that, another way of asking, why double prime, what function, if I take its second derivative, I get that e to the ix. That does work. E to the ix. And so here, if I take that, I get e to the I, e to the ix. And then here, if I take the double prime, e to the I squared, e to the ix. And so this indeed equals. So this indeed does work. So here's another solution. Is it a solution I was looking for? No. Thank you. I hate playing this game. It's like, please guess what the professor's thinking. Here I have y equal to sine of x. And notice that these two guesses are not actually that far apart. And y equal cosine of x also works, right? And so we consider, and so we say we solve this by, we call that inspection. It says solve by inspection. That's what your book's going to label it. Please solve the following by inspection, right? So here, this is y double prime equals to I squared e to the I x. And so that's equal to negative e to the x. So that satisfies this. Does anyone know, just while we're talking about it, let me look this up. No, what am I looking for? I don't even remember the formula off my head, but there's. Here it is. Have you guys ever seen this before? Cosine of x is equal to e to the ix plus e to the negative ix over 2. And sine of x is equal to the e to the ix minus e to the ix negatives. You guys ever seen this mess before? So if you see e to the ix and all this other stuff, technically it's the same. Hopefully you've seen Euler's formula somewhere before. This e to the I theta equals cosine theta plus I sine theta. You seen this before? If not, I'll teach it to you in 2 minutes. So e to the ix is in some ways sine and cosine. So here, notice that sine works and cosine works, right? Let me just crunch through one because let me just crunch through one. So let me just type in sine of x double prime plus sine of x is equal to 0. And we just run through this. This becomes minus sine of x. 0. Okay. And so this works. But notice that since these two are linearly independent, we're gonna this one's fine, we can add it. We're gonna ignore this one for a second because if I add and subtract these two, I get this. Notice that here, if I have any constant a cosine x plus some b sine of x, this is also a solution, right? So y of any a cosine of x of any b is also a solution because this will just give me minus cosine. If I take its double derivative, so this will be minus a cosine of x. This will give me minus b cosine of x. and then it'll just cancel out. And so here I can take any combination of these two solutions. And that'll get us into the linearity principle. Now let me leave this for a second in case you want to write something down. I lost my drink. I legit lost my drink. Oh, there it is. It's like that's my fourth way of waiting. All right. Let's talk about the linearity principle. So linearity principle. So let y of h1 be a solution, let y of h2 be another solution. Then y can be any linear combination, that is, of those solutions. And so here I'll have C1 and C2 belong to real numbers. So these are just real coefficients, and H1 be H2. And we want these to be, and this only works if it's linear and homogeneous. We also want these two solutions to be linearly independent. Because if they're linearly independent, we call it a basis. But let me show you why it doesn't work in hopes that you will not try to attempt to do things that you will not try to use this later when it's not valid. So this has to be. So here we have the same ODE. And by inspection, we can get 1 plus cosine of x as a solution. Because if I take its derivative, I'll get minus sine of x, and I take that derivative, I'll get minus cosine of x. So it'll be cosine of x minus cosine of x. 1 plus cosine of x is equal to 1 because the cosines will cancel. And another solution, so here I'll have y1 equal to this, and another solution is y2 equals to this, and so I'll have 1 plus sine of x, right? And so here, notice here that if I take this derivative, I'll get cosine of x, and I take that derivative again, I'll get minus sine of x, and so I'll have minus sine of x plus 1 plus sine of x, so the sine of x cancels, and I get a 1. So both of these, but here even if I just add these up, right? If I say y is equal to y plus 1 sine of x plus 1 plus cosine of x. So I'm just adding them up, right? As simple as it can be. What do I have here? Is I have this is equal to 2 plus cosine x plus sine x. But notice here that this is not a solution because what I'd get here is I'd get 2 equal to 1. So this doesn't work. So linearity principle doesn't hold because here if I plug this in, it'll be 2 plus cosine x plus sine of x rho prime plus 2 cosine x sine of x, or plus cosine, got my little pluses, x equals 1, which means 2 does not equal to 1, so it doesn't work. All right, so let's look at something here. Let's look at something here. Here's a bad nonlinear. This isn't linear because I have y double prime times a y, right? Now, by inspection, you can get one of the solutions, right? Here I'll have x squared. So let's test it real quick. Let's type in x. X squared. See if this works. Hold on. Yes, it should work. So what do I get here? So if I test the solution, I have x squared double prime times x squared minus x times x. Oops, don't actually do the prime. X squared prime. I want this equal to 0. This is homogeneous, but it's not linear. However, when I do this, I'm going to get 2x squared, so it just becomes 2x. This gives me 2x squared. This gives me 2x, and so it'd be minus 2x squared, which is equal to 0. But notice here, even if I take this simple thing, the simple answer here, and say y2 and just put a constant in front of it, 3x squared, this no longer works because here the 3 would exist twice, and here it only exists once, and so they no longer clearly cancel. Okay. And so it has to be linear and homogeneous. If not, you cannot use this linearity principle. All right, so let's talk about actually solving things. So here we're going to solve initial value problems. So initial value problems with a basis and a general solution and a particular solution. So here we're going to be given a linear homogeneous problem. We're going to give some initial conditions. The initial conditions can come in two forms. We can either have they can come in two forms. They can either you can have some point and a derivative at some point, right? And so, or you can have, oops, that shouldn't have a derivative sign on it. Sorry about that. So I can have a point and a derivative at some point, right? Or I can just have two different points. Either way will give you a solution. So when we solve it, we get this general solution. And then if we use our, whatever our initial conditions are, we'll get what we call the particular solution. So solving for initial conditions, we get a particular solution. So if I actually have values for C1 and C2, that's a particular. If I leave it in this form, it's general. Here, yi form the basis of being a linearly independent solution. And so that means that y1 needs to be fundamentally different than y2. And if these two are truly fundamentally different, you should be able to handle any initial conditions you're given. If they're not, it doesn't work out. So, and I'll show you how to get those in a second. So let's solve this initial value problem with this. So we found out from our previous that the general solution for the following was a cosine x plus b sine of x. Thanks. So we have that initial condition. Do I have the answers of this one? No, I don't. That's fine. I'll just crunch it through anyways. So let's woohoo. That should not be a plus. That should be an equal sign. So here we have y naught of 0 is equal to 3. And so we're going to plug that in to figure out what our initial value, what the particular solution. So here's the general solution. This is the general solution. General solution from previous problem. Previously found. And so we're going to use that to find the general solution. So here, we're just going to take 3. And so this is equal to a cosine of 0, which is 1, plus b sine of 0, which is 0. So this is 0, right? So that this implies that a is equal to 3. And then we'll do y prime of 0 is equal to minus 0.5. And that's going to equal to, now if I take the derivative of this, so derivative of cosine is minus sine, so this will be minus a sine x plus sine becomes cosine, so this would be b cosine. Oh, and x, we know what x is, it's 0. So let's plug in the 0, 0, and the 0. All right, so sine of 0 is 0, so I get rid of this, and then cosine is just 1, so this just implies that b is equal to, oops, negative 0.5, and then I have my particular solution of y is equal to 3 cosine x minus 0.5 sine of x. And so once we found the coefficients here, we have our particular solution. And we call this the particular. Particular solution. Okay. All right, let me let in my dog. It's whining at me. Did you write that down? What you two? Come on, get in here. Come on, try and teach. Doggos. Yes, yes, that's my foot, dog. Dog, I can't play with you. Jeez. See these people? They need to be taught. All right, that's plenty of time to write that down. All right, so let's do this. This is something I want to show you, but I will not test you on. You'll do a couple of homework on it. And it's called reduction of order. And it's, when I first taught this class and I read through this book, I had to read through it like 4 times. I'm like, what is this book saying, right? I'm like, I don't even know. And then I worked through it a couple times, like, okay, I finally get it. So let me try to walk you through it. If it ends up being a little bit more of a disaster than I hope, I'll try to give you kind of the general sense of what goes on here. But I do not want to spend time on this. I will not ever test you on this. I just want you to see it. It's one of those things I want you to have seen and done a couple homework problems on. Okay. All right. So let's do this. So if given the solution of a second order linearly independent of a second order, given one solution, a second linearly independent solution. No, I don't need the order here. Sorry, it was written correctly. Can be. Oh, I think I copied this from the book. That's why I should not say anything. The author is a wonderful man. Just some days I read through this book, I'm like, was this English, or was it got translated in English? Given one solution, a second linearly independent solution can be attained by solving a first order ODE. This is called the method of reduction of order. All right, so we find one by inspection, right? That means guess one, really what it means. So here, if I was going to try to figure out what's an answer here, if you hum and haw long enough, you'll get y1 is equal to x. Because if I plug in x here, this ends up being 0, right? This ends up being 1, so it'd be minus x plus x is equal to 0. So you can see that x equals 1 is the solution. So once we have that, so once we know it's a solution, we can then substitute to find another. So here we say y is equal to some u times y1. And in this case, it's equal to u of x. Okay. And you just make this declaration. It's never explained to you. It's not even really well explained to me, and I've studied this for a while. You find its derivative, and you have u of x. So if I take the derivative of this, it's u prime x plus u. So we've done something like this before, where you take its derivative, you get this, and then since this is just x, it ends up simplifying quite well to this. And then we need to take its second derivative. Well, if we take the second derivative here, this becomes u prime x plus u prime. And then hold on, but I need to do one more. 3 plus u double prime x. Okay, so this is, I use product rule here. So this becomes u prime, and product rule will give me, hold on, no x here. So product rule will give me u prime, and then 1, and then double prime x, and then you can add these two up. So I get u double prime x plus 2u prime. All right. And so what do? We just plug this into here. So we're going to have x squared minus x. And this becomes u double prime x plus 2u prime minus x. Y prime is u prime x plus u. plus ux, that's what we're setting y equal to 0. Once we do all this, we distribute and simplify. Here we get x prime minus x, u double prime. I'm going to skip the simplification. If you need me to go through all the other steps, come to office hours. I want to spend more time on stuff I'm going to really grade you on, but I do want you to see this. X minus 2 u prime equal to 0. And notice that this negative x goes into here and this in here, and this cancels out, and you end up with, and so we get a reduction of order. Because then we can just say, here we just say v is equal to u prime. We rewrite this as x squared minus x, b prime plus x minus 2. My computer's getting crunchy. B equal to 0. And this is linear. In fact, because you can divide this out, this becomes linear. And you can solve for it. And so let's do that. So that means, in fact, we can just put it this way. We can have u and so here, I'm going to minus this across. Let me not skip this step. Divide this out. So I have v prime over v. So divide this out, minus x minus 2 over x squared plus x. And then here, we'll just integrate both sides. So I get ln of v is equal to ln of x minus 1 minus 2 ln absolute value of x. I'll go. Getting hungry. That's what's going on. Let me finish this real quick. I'll feed it as we're switching notes. Squared. All right. Since we put these two together, that means v. I'm taking that away from you. Reason you're making enough noise to kill me. I know. Feed you in 2 seconds, dog. If your dogs do that, just grab his food bowl and chuck it at you. Feed me, human. I don't care if you're working. Oh, man. I feel really, really bad for the, you know, I just have 2 dogs. You know, people have like little kids at home, you know, and they still have to teach. I mean, my 2 dogs, I can just check them out, go outside and be that way, right? All right, so this, and then, so you switch out u, so u prime is equal to x minus 1. You do this song and dance again. I'm not gonna spend all this time on it. It's just, we're not gonna do it that often. You do the same thing, and then you solve for u, and you get u is equal to the following, and you get u is equal to ln of x, absolute value of x plus 1. So this is the reduction of order method. Okay, so I'll leave this up.